On a September morning in 2017, a spacecraft the size of a school bus tilted its antenna one last time toward a planet it had circled for 13 years. It had no fuel left to fight gravity anymore, and within minutes it would become part of the very world it had spent its entire working life studying. This was not a malfunction. It was not an accident born of failure. It was a plan, carefully designed, years in advance by teams of scientists and engineers who understood that even an ending could be turned into an opportunity for discovery. This is the story of Cassini, one of the most ambitious robotic missions ever sent into the outer solar system, and of the extraordinary science it produced, not despite its death, but precisely because of how deliberately that death was engineered. To understand why Cassini's ending mattered so much to the world of space science, it helps to go back to where the whole journey began. On October 15, 1997, a Titan IV-B Centaur rocket lifted off from Cape Canaveral, Florida, carrying a spacecraft that would go on to rewrite much of what humanity understood about Saturn. Strapped to Cassini was a smaller companion, the European Space Agency's Huygens probe, destined to become the first human-made object ever to land on a moon in the outer solar system. The target of this journey was Saturn itself, the magnificent ringed giant sitting nearly 1 billion miles from Earth, so distant that sunlight takes over an hour just to travel from the sun to its clouds. Getting there was never going to be simple or quick. Cassini did not travel in a straight line toward its destination. Mission engineers instead plotted a long, looping, gravity-assisted trajectory that sent the spacecraft swinging past Venus twice, then Earth, and finally Jupiter, using the gravitational pull of each planet like a slingshot to build up speed while conserving as much onboard fuel as possible for the years of operations still to come. This kind of careful orbital choreography meant patience was required. Nearly 7 years passed between the moment of launch and the moment Cassini finally arrived at Saturn. That arrival came on the night of June 30, 2004, when Cassini fired its main engine and slipped smoothly into orbit around Saturn, becoming the first spacecraft in history to do so. It was an enormously risky maneuver. A single failure during that critical engine burn would have sent the spacecraft sailing helplessly past Saturn and off into deep space, its entire mission over before it had truly begun. Instead, the burn worked exactly as planned, and a new era in the study of the Saturn system opened up. What followed over the next 13 years was a sustained, patient campaign of observation, watching Saturn's turbulent atmosphere shift and storm, mapping its powerful and puzzling magnetic environment, studying the fine architecture of its dazzling rings, and cataloging its enormous family of more than 60 moons, ranging from tiny, irregular fragments of ice barely a few miles across to Titan, a moon larger in size than the planet Mercury. Before turning to the dramatic circumstances of Cassini's ending, it is worth pausing to appreciate just how profoundly the mission had already reshaped our picture of the Saturn system while it was still healthy and fully operational. In January 2005, the Huygens probe detached from Cassini and parachuted down through Titan's thick, hazy, orange-tinted atmosphere, eventually coming to rest on a frozen, pebble-strewn plain unlike anything humans had ever photographed up close. It remains to this day the most distant successful landing ever achieved by a human-made spacecraft, and the images it beamed back showed a landscape eerily reminiscent of a dry riverbed on Earth, a channel carved not by water, but by liquid methane and ethane flowing across an alien surface. Cassini's own instruments, continuing to orbit high above for more than a decade afterward, confirmed something remarkable about Titan. The moon has genuine lakes and seas of liquid hydrocarbons pooling on its surface, complete with what appears to be an active rain cycle, evaporation, and seasonal transformation echoing Earth's own water cycle, just built from entirely different chemistry. Titan remains the only body known anywhere in the solar system, apart from Earth itself, confirmed to have standing liquid on its surface, making it a strange, frigid mirror of home, familiar in shape, yet utterly alien in substance. Perhaps the single most electrifying discovery of the entire Cassini mission, however, came from a small moon that few scientists had expected much from at all. Enceladus, a brilliantly white, ice-covered world barely 300 miles across. In 2005, Cassini's cameras spotted something nobody had anticipated, plumes of water vapor and fine icy particles erupting dramatically from a set of long cracks near the moon's south pole, jutting hundreds of miles out into space. Io. In the years that followed, Cassini's controllers grew bold enough to send the spacecraft diving directly through these plumes on repeated flybys, and the instruments on board detected salts, complex organic molecules, and even tiny grains of silica consistent with ongoing hydrothermal activity occurring somewhere on a rocky seafloor deep beneath the ice. The implications of this were staggering. Hidden beneath Enceladus's frozen shell lies a global liquid water ocean, kept liquid and warm by the constant tidal flexing produced by Saturn's powerful gravity, and quite possibly in direct contact with a rocky core, the same basic combination of ingredients that scientists associate with the conditions that gave rise to life here on Earth billions of years ago. Almost overnight, a small moon that had barely registered on scientists' list of priorities became one of the single most promising places in the entire solar system to search for life beyond our home planet. Cassini's long residence at Saturn also completely transformed scientific understanding of the planet's famous rings, which turned out to be far more dynamic, layered, and structurally complex than the simple flat disks so often shown in textbook illustrations. The spacecraft revealed that the rings are composed of countless individual chunks of ice and rock, spanning an enormous range of sizes, from grains no larger than a speck of sand up to boulders the size of houses, all sculpted continuously by small embedded moonlets, whose gravity carves visible propeller-shaped gaps as they travel through the ring material. Delicate waves rippling outward through the rings even carried information about vibrations occurring deep inside Saturn itself, effectively turning the entire ring system into an accidental seismograph for the planet it surrounds, a completely unexpected way of probing a world's hidden interior from a great distance. By the time Cassini had spent more than a decade at Saturn, it had already reshaped nearly every chapter of the scientific understanding of this part of the solar system. Yet its single most consequential chapter of all was still ahead of it, and reaching it required the mission itself to come to an end. By the year 2017, Cassini was running critically low on the small amount of rocket fuel it relied on to control its orientation and adjust its orbital path around Saturn. Left uncontrolled and adrift once that fuel ran out completely, the spacecraft would eventually have followed an unpredictable trajectory around the planet, and mission planners recognized a real, if distant, risk that it could one day collide with one of Saturn's ocean-bearing moons, such as Enceladus or Titan. That risk, however small, was simply unacceptable to the scientific community. Even a spacecraft that had been dead and drifting for years could still be carrying traces of hardy Earth microbes that had somehow survived the long journey clinging to its structure since the moment of launch 2 decades earlier. If Cassini ever drifted into Enceladus and contaminated that pristine, potentially life-bearing subsurface ocean with organisms from Earth, it could permanently compromise humanity's best chance of one day searching that very ocean for signs of alien life. Faced with this risk, mission planners made a deliberate and carefully reasoned choice years in advance of the actual event. Rather than simply switching Cassini off and leaving its ultimate fate to chance, they would instead fly the spacecraft directly into Saturn itself, guaranteeing that it along with any microscopic hitchhikers it carried, would be destroyed completely and harmlessly high in the planet's thick atmosphere. But NASA had no intention of letting this ending be scientifically wasteful. If Cassini absolutely had to end its life, mission planners were determined that it would end that life doing science that no other spacecraft, before or since, had ever been able to attempt. The plan they eventually designed became known within NASA as the Grand Finale, and it succeeded in turning what began as an unavoidable engineering necessity into one of the boldest and most scientifically rich campaigns of the entire 13-year mission. In late November of 2016, Cassini used a close flyby of Titan to bend and reshape its orbit, beginning a new phase of operations that engineers referred to as the ring-grazing orbits. Over the months that followed, the spacecraft swept repeatedly just outside Saturn's narrow F-ring, passing closer to the ring system than it had ever dared to fly before, capturing extraordinarily high-resolution images of delicate ring structures and threading its way past tiny embedded ring moons such as Pan and Daphnis at closer range than any previous flyby had attempted. Then, on April 26, 2017, Cassini used one final close pass by Titan to dramatically reshape its trajectory once more, a maneuver that flung the spacecraft entirely up and over Saturn's icy ring plane and set it on an entirely new course, one designed to thread the narrow, largely unexplored gap between the planet's own cloud tops and the innermost visible ring, a gap roughly 1,200 miles wide that no spacecraft in the history of space exploration had ever dared to enter before. Nobody could say with total confidence what exactly Cassini would find inside that narrow gap. Saturn's rings are composed of billions upon billions of individual ice particles, and even a single stray grain striking the spacecraft at the tremendous orbital speeds involved could, in principle, have proven catastrophic to the mission in an instant. As a precaution against this danger, engineers reoriented Cassini's large dish-shaped communications antenna to face directly forward during each and every ring plane crossing, effectively using it as an improvised shield to deflect any small particles that might otherwise strike more sensitive parts of the spacecraft. Beginning on April 26, 2017, Cassini plunged through this narrow gap for the very first time in its history, then repeated the same daring maneuver again, the following week, and again the week after that. In total, across roughly 5 months, the spacecraft completed 22 of these weekly dives, each one threading the very same narrow space between Saturn's swirling atmosphere and the innermost edge of its rings, and each one gathering an entirely new category of scientific data that had simply never existed before in the history of planetary science. These 22 extraordinary dives amounted to almost an entirely new mission, quietly stitched onto the tail end of the old one, and the data they returned began rewriting scientific understanding of the Saturn system almost immediately. By very carefully measuring the total mass of the ring system, as Cassini repeatedly passed directly through the gap, scientists were able to calculate that Saturn's rings weigh considerably less than earlier estimates had suggested, and that they contain relatively little of the dark, non-icy material that would be expected to accumulate steadily on their surfaces over billions of years of exposure to space. This pointed toward rings that might be startlingly young in cosmic terms, perhaps only a few 100 million years old, meaning that dinosaurs may already have been walking the surface of the Earth by the time Saturn's rings first began to form, a possibility that reopened long-standing scientific debates about exactly how and when this magnificent ring system originally came into being. Instruments aboard Cassini also detected steady streams of icy, organic-rich particles raining continuously down out of the rings and directly into Saturn's upper atmosphere, a slow but steady process that is gradually eroding the ring system from within, while other measurements revealed clear evidence of electric currents flowing along magnetic field lines that physically connect the rings to Saturn's own atmosphere, a direct physical link between the planet and its surrounding halo of ice that had never before been measured so precisely. A completely new radiation belt was also discovered, trapped within the gap between the rings and the planet itself, formed as high-energy cosmic ray particles struck the icy ring material and produced a cascade of secondary particles in the process. By carefully tracking tiny, subtle changes in Cassini's own trajectory as it swept close past the planet during each of these final orbits, scientists were also able to measure Saturn's gravitational field with a level of precision that had simply never been achieved before, allowing them to estimate just how deep the planet's famously powerful winds actually extend beneath its visible cloud tops, and to substantially refine long-standing models of the planet's hidden interior, which now suggest that Saturn's core may be considerably larger, fuzzier, and more diffusely mixed with the surrounding layers of hydrogen and helium than the small, compact, sharply defined rocky core that scientists had traditionally assumed gas giant planets possessed. Cassini's final measurements also confirmed a genuinely puzzling result concerning Saturn's magnetic field, revealing that it is almost perfectly aligned with the planet's own axis of rotation, showing essentially no detectable tilt at all. This finding is deeply puzzling to planetary scientists because prevailing dynamo theory holds that a planet's magnetic field generally requires at least some small degree of tilt in order to keep regenerating itself continuously over geological time. Rather than resolving this long-standing mystery, Cassini's remarkably precise close-in measurements only deepened it further, leaving it as one of the most intriguing open questions the mission left behind for future researchers to eventually solve. It is worth emphasizing that every single one of these landmark findings depended entirely on Cassini's controllers being willing to fly the spacecraft somewhere genuinely dangerous. Somewhere no previous mission planner would ever have risked sending an operational, healthy spacecraft. A mission designed purely around the principle of self-preservation would never have collected any of this remarkable data. By September of 2017, the 22 grand finale orbits had all been completed, and the spacecraft itself had only a matter of days left before its planned end. On September 11th, Cassini captured one of the most quietly poignant images of its entire mission, a final view of Titan's North Polar region, its surface mottled with dark lakes and seas of liquid methane, glimpsed one last time during a distant farewell flyby that the mission team affectionately nicknamed the Goodbye Kiss, since it was this very same flyby's gravitational pull that would go on to set up the precise trajectory for Cassini's final plunge into Saturn just days later. 2 days after that, on September 13th, Cassini's cameras assembled one final sweeping mosaic of Saturn itself, stitched together as the spacecraft made its slow, deliberate way toward its very last encounter with the planet it had called home for over a decade. Then, on September 14th, the day immediately before the mission's end, Cassini captured its very last photograph of all, a wide, visually unremarkable patch of Saturn's swirling atmosphere, notable only because it marked the exact precise location where the spacecraft itself was calculated to enter that atmosphere roughly 24 hours later. In its very final hours, Cassini's mission team made one last decision that speaks powerfully to the spirit of the entire endeavor. Rather than devoting the spacecraft's last remaining reserves of power and fuel purely toward capturing dramatic final photographs, they instead configured Cassini to prioritize keeping its scientific instruments actively running, and its antenna pointed steadily at Earth for as long as physically possible, right up until the moment atmospheric forces made that simply impossible to maintain any longer. Cassini would spend its very last minutes of existence not looking outward through its cameras, but sensing directly through its instruments, actively sampling the composition of the very atmosphere it was falling helplessly into in real time. for as long as it could possibly keep transmitting those precious results back home across the vast gulf of space. In the pre-dawn hours of September 15, 2017, Cassini finally crossed into the outermost layers of Saturn's atmosphere, traveling at a staggering speed of roughly 70,000 miles per hour, more than 20 miles covered every single second. For approximately the first minute of this final descent, Cassini's small attitude control thrusters fought valiantly to keep the spacecraft's large antenna pointed steadily at Earth, even as the rapidly thickening atmospheric gas around it began to buffet and push the spacecraft increasingly off its intended course. The onboard computer worked continuously to compensate for this growing turbulence, firing its thrusters at their absolute maximum strength in a desperate effort to hold Cassini steady, all while its scientific instruments sampled the actual composition of Saturn's atmosphere directly for the very first time in the mission's entire 20-year history, faithfully radioing those unprecedented results back across nearly 1 billion miles of empty space toward Earth. Remarkably, the spacecraft held on considerably longer than its own engineers had originally predicted it would, continuing to transmit valuable data for roughly 30 additional seconds beyond the precise point at which controllers had expected its overworked thrusters to finally lose their desperate fight against the atmosphere. Then, at last, the overwhelming atmospheric forces finally won out completely, and Cassini's carefully maintained signal, a signal already delayed by the 83 long minutes it took simply to cross the vast distance separating Saturn from Earth, simply and abruptly stopped. Inside the control room at NASA's Jet Propulsion Laboratory and at the enormous Deep Space Network antenna located in Canberra, Australia, that had been faithfully listening for that signal, the room fell completely and instantly quiet. At exactly 7:55 in the morning Eastern Time, mission controllers formally confirmed what everyone present already understood in their hearts to be true. Cassini's transmission had permanently ended. Somewhere out there, nearly 90 minutes earlier in real time and roughly 1 billion miles away in physical distance, the spacecraft had already burned violently apart within Saturn's dense atmosphere like a meteor streaking across an alien sky, its metal frame and delicate electronics vaporizing completely into the very planet it had spent 13 devoted years patiently studying from orbit. Its extraordinary mission, spanning nearly 20 full years and more than 7,000 consecutive days in space since its original 1997 launch from Cape Canaveral, was finally completely over. It would be easy, looking back, to think of Cassini's final plunge as nothing more than a dramatic, cinematic farewell, a fitting and emotionally satisfying way to bring a long and successful mission to its natural close. But the deeper truth is that the grand finale accomplished considerably more than simply providing an emotionally resonant ending for headline writers and space enthusiasts alike. It fundamentally and permanently changed how scientists think about several genuinely core questions in the broader field of planetary science. It thoroughly rewrote long-held assumptions about the age of Saturn's rings, transforming what many researchers had long assumed was one of the oldest and most ancient structures anywhere in the solar system, into something that may instead have formed relatively recently in cosmic terms, forcing scientists to develop entirely new theories involving violent past collisions or the gradual tidal destruction of some now vanished moon to explain the ring's surprisingly youthful composition. It gave scientists their very first direct, hands-on taste of a giant planet's atmosphere sampled from the inside, rather than relying purely on remote sensing conducted safely from orbit, data that will directly inform how NASA engineers eventually design future atmospheric entry probes intended for even more distant and poorly understood gas giants such as Uranus and Neptune, worlds about which humanity still knows remarkably little. It firmly established the careful practice of planetary protection as a genuinely serious engineering requirement. rather than a mere afterthought tacked onto the end of mission planning, and the core idea that a spacecraft's eventual disposal deserves every bit as much careful, advanced planning as its original journey has since become a template that other ambitious missions, including several currently being planned for Europa and other potentially ocean-bearing worlds, now follow closely as standard practice. And finally, it left behind an enormous, genuinely still active scientific legacy that continues to yield new results even today. Cassini gathered such an extraordinary volume of data across its 13 years in orbit around Saturn. More than 453,000 individual images alone, along with literally hundreds of thousands of hours of continuous scientific observations that researchers around the world are still actively combing carefully through that vast archive today, years after the spacecraft itself physically ceased to exist, continuing to extract fresh discoveries from data that was collected long before their own current research projects even began. Cassini did not have to end its remarkable life in quite the dramatic way that it ultimately did. Engineers could easily have chosen simply to let the aging spacecraft drift gradually into permanent silence instead, its fuel finally exhausted, its various instruments powering down quietly one after another in a slow, unremarkable, and largely undramatic fade into darkness. Instead, its carefully planned final act became one of the single most scientifically valuable chapters of the entire mission. A deliberate and carefully calculated risk that successfully turned an otherwise unavoidable ending into one final glorious act of genuine scientific discovery. In choosing quite deliberately to fly directly into danger rather than cautiously away from it, Cassini's dedicated mission team ultimately ensured that even the spacecraft's own death served exactly the same fundamental purpose as its entire 20-year working life had: to teach humanity something genuinely new about the vast and mysterious universe we all live in together. Nearly 1 billion miles from home, a small and determined robotic explorer finally became a permanent part of the very planet it had spent so long learning to love studying. And in doing so, it profoundly changed not only how we understand Saturn itself, but also the very way we now choose to end any mission that never truly wanted to stop learning in the first place.